My name is Nakul and I would like to welcome you all on a talk about distributed tracing. I would like to kick off this talk by discussing why even we should bother about latency and what role it plays in distributed system. After that, we will take a look on what distributed tracing is and what it can offer us. Then there will be a short demo just to get a feel about distributed tracing. Next, we will discuss what Zipkin really is and take a look on few of its core concepts. And finally, I would like to walk you through the code that I use for the sample the demo used during the presentation. So what is latency? Well, we may define it in simple words as the amount of time it takes to complete a particular task. Every action that we perform takes some amount of time. For example, let's say it takes 2 hours for me to fly from city A to city B. So in this case, my latency is going to be 2 hours. Some people tend to believe that improving throughput is going to somehow make a positive impact on their latency. Well, it's really not the case. So coming back to my example of flying between 2 cities, improving throughput means instead of flying 1 plane, let's fly 10 planes in parallel. So now we can carry more number of passengers from city A to city B. However, my latency, that is overall time for a particular passenger, remains the same. In computer, every operation that we perform takes some amount of time. For example, if we want to access the L1 cache or L2 cache, acquiring a lock, releasing a lock, seeking something from the disk, accessing the main memory, it all takes some amount of time. Maybe the amount of time is so small that it's almost negligible for a human eye, and maybe if you don't have huge traffic, you really don't bother about all those small operations which computer take. But when you are hit with a huge scale, then all those small operations starts to add up, and that's really when you started to kind of scratch your head and try to worry about things. So who cares about latency in general? Well, it's an end user who cares about latency, or who is, let's say, impacted the most because of slow applications. But the funny thing is that they are not sitting with a stopwatch to measure how fast your application takes to react. On the contrary, they are driven by their needs. And they just want to interact with your application to do with their some sort of job and be happy. But in some cases, speed is the name of the game. So if we are building some trading systems, in that case, low latency can make a difference between grabbing an opportunity or losing an opportunity. So the point I'm trying to make here is that the users generally don't care how fast your application responds, but they tend to start to notice when things starts to get slower. What is so fascinating about distributed world is that in a distributed system, a single request may end up touching hundreds of services running, written in different programming languages, deployed across various runtime environment, and maybe potentially using hundreds or thousands of machines. In monolithic world, we could somehow squeeze all this information in our head and use some architecture diagram, some documentation, and maybe have a current look on our production environment, how it looks like thanks to those documents, and maybe go to them when we have some production issues and try to figure out where to look for. In microservice world, the picture is ever changing. New services can spin up at no time, old services can be removed, and some can be upgraded to improve the performance. So it's really hard to catch up, and also it's really difficult to put all these things in the head. And what happens when things starts to get slow? Well, we can guess. There is no harm in guessing, but guessing don't solve the production issue, unfortunately, because there are too many moving components at the time. So let me tell you now a story about a Bob. Bob is a programmer who recently used microservices to migrate their legacy application to address their new business needs. Recently, he started receiving a bunch of emails every day from random customers complaining that, well, your system is working really slow. And since there can be many potential reasons for such problems like slow I/O, networking error, slow queries, maybe garbage collector is kicking in at some odd times, he simply had no idea where to start looking for the problem. What Bob didn't knew that time was that he was suffering from long-tail latency. Nevertheless, he tried his level best to somehow come up with some solution to solve those problems. So his first attempt was to go and look into the logs, because that is what was available to him. So due to large number of services, one may end up with lots and lots of log files. And what happens is when we start to dig into the logs, we can encounter an overwhelming amount of information and also a lot of noise that may distract us. For example, thread dumps, async, some stack traces. Moreover, not every service we need to examine in order to resolve some problems, because some of them are not in the critical path. For example, let's say there are few services which are asynchronous by nature, and what happens is when you make a request, they receive the request, they say, all right, you get it 200 response, and they start some background job. So to understand the critical path is really important in a distributed system. If we have so much information, then also we need to correlate them, because the services may be running on different servers or different clusters or different zones. And when we want to correlate all these, it takes some manual amount of work. Lastly, we are ended up with some bunch of numbers. And what to do with them? Well, they simply don't make sense. Why? Because we can take their mean, median, mode, standard deviation. What to do with those bunch of numbers? So this approach didn't lead him to some, let's say, productive results which he could use in order to resolve his problems. So the second option he used was about matrices. Well, matrices in general are good. They can say something is wrong, but unfortunately they can't tell the cause. They can't tell what is causing this problem. Furthermore, the way in which we aggregate those data and plot them may deceive us. Why? Because, for example, consider a city where 1 million people are living, and one person is making $20 million a month, and others are making $1 a month. Now, if you take the average of the income there, you will get an idea that, well, the people are maybe not so poor, but which is far away from the reality. The same happens if we try to take the average of latency and try to plot it. It's not going to give us some very productive insight, and may deceive us even believing that the problem is not so terribly worst. So at that time, the Bob started to think, well, first my problem is to find how many clients are really impacted at this moment by the problem. So that's where he learned about percentile, and percentile is a statistic that identifies the percentage of the data that is less than a given value. To be more precise, Bob was interested in the 99th percentile of his system, and 99th percentile means that 1 out of every 100 visits in the system experience some delay D. In this case, it can be a 50 millisecond delay. So if we want to calculate the total number of visits which are experiencing the delay, we can calculate using a simple formula, and we get, well, some number, in this case 5,000. As you can see, this number is not looking such alarming at this very moment. I mean, 500,000 visits, and we have only 5,000 visits experiencing the delay. However, Bob was dealing with a distributed system, which means that a single visit in his system was ending up making 8 downstream calls, which were interacting with some service S, which was highly active service. It was 99% fast, but only 1% slow. So now, taking this into consideration, the likelihood of encountering latency-related issue can be calculated using 1 minus 99% is expressed as 0.99 to the power of number of downstream calls. So here are 8 downstream calls, so that's why we have 8 here. Doing the maths, we reach somewhat about 8%. Now the total number of visits which could be affected by this problem, as you can see, is 8% of n, which is 40,000. So all of a sudden you can see this number is really starting to rise up. And to make the situation more worse, this is not the unique visit that only 40,000 customers are going to experience this delay. This means that any customer who is visiting our site might experience this delay depending on the time of the day. Lastly, this number, 40,000, is directly dependent on the performance of this service and also the number of downstream calls, how many downstream calls we are making. So Bob was happy. Bob said, finally, I made some success. So he wanted to share his findings with the boss. So he went to the boss, and he said, boss, I know something about the problem. So, but Bob said that, well, I really don't care about the problem, how many customers are impacted, just go and fix it. Um, so Bob went back to his table and he started to think, well, I still don't know many things. And uh, one of them was request timeline, which means how many operations were invoked, which services were touched, and how many of them were in critical path. He didn't know how to correlate the logs, how to make sense out some of the information. He also was interested to run the same operation on various clusters and see whether the same operation performs slow on every cluster, or maybe on half of the cluster, or maybe for some specific zone. But he didn't have any tool to do that thing. And even if he would execute and fire those requests, he could just use some log dot entering and enter there some time and log dot leaving. So it was not really helpful to get some insight value. Uh, Also, if there were some delays experienced by the customer, then he was really curious how much these delays are, how much really this slowness factor is. And he wanted to compare this slowness with the acceptable value, which they have somehow set it for the customer. And last but not the least, he wanted to know how all the interaction looks like in terms of call graph when this problem started to spin up. So Bob at that time was missing distributed tracing. What distributed tracing can do? Well, it tracks request flow for us. So the tracked data is available within minutes, which led us to react really fast. Moreover, thanks to dynamically instrumentation, we have to do minimal configuration in order to incorporate it with our production environment. The collected data contains lots and lots of valuable information, such as the name of the services, the name of the operations, how much time they took, how many times they were invoked during the life cycle of a single request. Using all this data, we can calculate or measure end-to-end latency. And not only this, we can perform some sort of call patterns optimizations. And bug discovering, which means, for example, let's say I'm making a request every time to a service, and in reality, this service results can be cached. Maybe I can, rather than throwing 10 or 20 calls, I can optimize them. Or sometimes there is a bug in implementation. The service was meant to be asynchronous in nature, but maybe the programmer have made some programming bug, and this was, let's say, he forgot to use some executor service or some thread pool, and they were executed synchronously. So how can we apply this knowledge if we know that distributed tracing can help us? Well, the answer is simple, via tracing system. So a tracing system should be able to trace, and when I mean trace, I didn't mean that it should be able to trace for a particular language and set of cluster and nodes. No, it should be able to trace irrelevant of the programming stack you are using. And also different runtime environment. So in a nutshell, it shouldn't tell you that only use Java for programming language, or use Python or Go or Scala, whatever. You can mix all those language, and it should still able to trace everything. It should have the low overhead. Why? Because we don't want to bring our production down because we are tracing some additional information. It should be scalable to address our business needs. Also, it should work round the clock, 365 days a year, or if it is a leap year, 366 days in a year, because production bugs are really difficult to produce. You don't want to miss them. And it shouldn't rely on programmers' collaboration, because if it requires programmers to log something in a specific format or do something clever from their side, then it defeats the purpose of our tracing system, which means that it should work and trace everything on production flawlessly. So let me introduce you now OpenZipkin. OpenZipkin implements distributed tracing. It is created by guys from Twitter, and it is based on Dapper, the paper published by Google. OpenZipkin is a GitHub organization. So basically, they took the Zipkin, they fork it, and they remove the bits from the Twitter and make it available for every one of us in a more generic way. It is open source, and it have a pluggable architecture. The pluggable architecture is really important here, because thanks to this, we can use OpenZipkin with our production stack and start to leverage the existing knowledge which our team have, rather than learning something new here. And I will show you just in a minute how the pluggable architecture works. one thing which we all should become familiar when we are speaking about Zipkin or distributed tracing is span. What is a span? Span denotes a logical unit of work done. The work done is expressed in human readable string. For example, create catalog, calculate price, foo, bar, whatever you want. It is a human readable string. They are created by tracer, which is an instrumented code, and we will see what tracer is in a couple of slides. They carry only minimal amount of information. That's why they are super, super, super slim, and they can be created really fast and stored really fast. One thing which is important to notice is that when an initial span is created, it is called a root span, which means a span without a parent ID. I will like to move to a demo on a couple of slides, but in order for all of us to follow along the demo, this concept is really important for Zipkin annotation, and it led me even to find a bug when I was preparing a demo for this presentation and submit it on GitHub, and now it's finally get resolved. So what happened is we have a client and a server. A client wants to request something from the server, and it makes an HTTP request, let's say for get catalog. When it makes the request, the Zipkin marks it as the beginning of the span. So the span gets started. The server receives the response, and when it receives the response, we can use the time to calculate the network latency, which means the time at which the server received the request minus the time at which the client sent the request. If we subtract them, we can get the network latency. After some time, server may start processing your request in order to generate some response. And in order to calculate the processing time, we can use SS minus SR, which means server sent minus server received, the time at which the server received the request. Finally, the server hands out the response back to the client, and client finally receives the response. At this time, we can again, the Zipkin marks the end of the span, so span gets closed at this time. The network latency we can again calculate using the time at which the client received the response minus the time at which the server sent the response. The overall response time can be calculated using CR minus CS, which means the time at which the client received the response minus the time at which the client sent the request. So as I told you that it lead me to something discover here, and this is the bug which I use the same information in order to file to GitHub because the time was not calculated properly. So it is really simple to follow through, and if you want to use Zipkin within your production environment, it's really not so complicated. You don't have to learn really lengthy documentation to understand how it works. Back to the slides then. Sorry. All right. So what happened when we made a HTTP request? What happened at the server side? Well, bunch of services came into the action. So one of the service was price service. So the catalog service asked the price service to calculate the price. The price service calculates the price. And then the catalog service asks some other service, which is called product service. Product service for the list of products. It consults the database, it performs some data analytic call, and finally hand out the response back to the catalog service. Now, all those green boxes which you see, they are called spans. So for every call which happen on the server side to external service, we have some spans created automatically by Zipkin. The collection of all those spans is what we call trace. One thing here is important to note that on my slides you see that span ID is 1 or 3 or trace ID is 1. They are simple numbers. Why so? Why it is not 100 or 200? Well, I didn't have a lot of room on my slides to put what Zipkin generates. What Zipkin does is Zipkin does not generate 1, 2 or some numbers like this. It is 64-bit or 84-bit or 128 bits of randomness. Why 64 or 128-bit? Because it depends on the version of Zipkin which you are using. And what is a trace? So trace is a collection of span, and if we want to be technically more correct, we can say it is a directed acyclic graph which helps to form the latency tree. So now at this moment, I would like to show you a demo application, how the Zipkin looks like and how we can interact. The code is at a GitHub. What I have done is I cloned the source code, and I'm running those applications locally. You can go to the GitHub, read the README, and you can replicate what I'm doing here on your local box. So back to here. All right. So the first thing I want to do is I have some service running on localhost port 8060, and I make some GET request, and the demo works in this case. So I get some JSON here. As you can see, I have some ID, some price, some products. But I haven't told you how this application works, so let's go to Zipkin and try to ask it whether it can investigate something for us, whether it can tell us something more about what happened when we made this GET request. So the very first thing which we can do is take a look on dependencies. So when I click on the dependency tab here, I can see that I have some catalog service which uses price service. As I click, I can see that it is used by the catalog service. And also I have some product service which uses two other services, Apache Spark and Mongo. And this full diagram is generated by Zipkin for me. So the next thing I am interested in is what happened when I made this HTTP GET request. So if I click Find Traces and I change the time, I can see here that I made a simple HTTP GET request here. And I can make one more just to show you that we can click Find Traces, and we can sort here also by newest, by longest, by shortest. So if I click here and I expand all, what happened is I made an HTTP request, as you can see here. And you can see here it is written 1. Why? Because of the fact that, as you can see, when I made this request here, I pass 1 as a parameter. So as you can see, that already I see that I made an HTTP request with some parameters. What happened then on the server, something called create catalog get invoked. So what happened there? We can click to find out some details there. So as you can see, I performed a couple of operations. So I fetched the price, products were fetched, and an email was sent. Also, without looking at the source code at this time, we can see that I'm using some sort of a circuit breaker implementation, Hystrix in this case. What was the class, what was the method, and what was the thread name which invoked it, and what is the local address. So all this information right now I have without even touching the source code. Next, what I did is someone called the price service, which means another HTTP request get invoked, and we calculate the cost. We can see that it is calculated by price service, and this method is invoked. In the similar manner, we call the product service, which means another HTTP call. We assemble the product, and we can see that we perform some select query and filtering. So far, so good. But let's try to simulate a scenario in which, for example, the server takes some more time to respond. So for example, here is a product number 2, and if I click, you can see that it is taking some time to return the response. And finally, after 3 seconds, I have the response. So now, can Zipkin try to help me to resolve what happened at this very moment? So I can click the Find Traces, and I sort it by newest first. If I click here and I say Expand All, what I can see here is this I will explain you later why Apache Spark is in this color on the next slide, but I want you to concentrate right now at this. So I can see here that cache for the price service was missed. So I want to know what happened. So as I can see that the cache was missed, the calculation time took some second. This is some random time. I hard-coded it in the source code. On which cluster the response or the request was processed, and so on. So I'm not limited here to this data. This data is added by me, and I will show you in the source code how we can add such data. So I can use this information to debug some problems. But you know, in life is not like so straightforward, and the production things goes crazy. Services goes down. So let's try to simulate a scenario now when we try to request something for which one of our service, let's say, encounters some major problem. So if I go to now Zipkin and say find traces, you can see all of a sudden that the color of my trace here is really different. So visually I can see that something really bad happened at this time. I can click here and I can say expand all, and this very time I can see, well, I had some problem with Mongo because of the color highlighting here. And if I click here, I can see, for example, which query got invoked. For example, db.products.find, maybe I fetch every product and it ended up destroying my services. So Zipkin, as you can see, doesn't kind of go down if one of your services is down. It tries to trace everything and show you in a visualizing form like this, or you can just use curl and get using API, all this on your command prompt and process it. All right, so this was one part of the demo. Now I would like you to focus on how Zipkin works internally, because it have really a pluggable architecture. So what happens when we run this demo? So we have some services, let's say catalog service, in which some instrumented code, the tracer is running. What happens is it collects and converts the span. The spans need to be transported between my service to the Zipkin, and we can use Scribe, Kafka, or HTTP to transport those spans. Then after that, the collector receives the span, and it deserializes, sample, and schedule them for storage. What storage does is it stores those spans in the DB, and we can use Cassandra, MySQL, or Elasticsearch right now. And this is the reason, for example, if you are not comfortable with Cassandra right now in your team, you can use maybe Elasticsearch in order to interact with Zipkin. So you are not forced to learn some new technology in order to just make use of tracing here. The API, on the other hand side, it retrieves the data from the storage, and its job is only this. So the UI finally uses the API service to visualize this data. And how all of this fits into the picture? Well, for example, if I want to interact only with API service, I'm not interested in visualizing those things. No one can, Zipkin allows me to do this. So for example, if I go here, and as you can see here, I'm calling API at the end. V1 means the number version 1, and I want to ask the list of services. So I click here and I see the list of services like Apache Spark, Go product, and so on. Please notice that the same list is rendered here. So we can fetch the same information. If you are doing some machine processing or something, you can fetch the trace and feed them for performing some sort of advanced stuff which makes sense in your case. Also, we can use the API to find out something more about Zipkin. For example, which version of Zipkin I'm running. Or I can monitor the health. What is the status, which type of collector I'm using, how much disk space it have occupied. Also, I can ask for the configuration, like right now, if you will see, I have limited the query only 10, and default loopback is this much time. And I'm instrumenting everything. Also, I can ask for some matrices, and here you can see that it exposed number of matrices, and I will show you during one of the slides that we can use these matrices to plot using Prometheus to monitor Zipkin. All right, so now let's focus on tags. What are tags? So tags are the key value pair. For example, calculation time, cluster, miss. What we can do with tag is, let's say if you want to debug some information, you want to put here the information which will make most sense when you encounter some problem. It doesn't mean you should write everything here, every little tiny bit of details. No, just think about what is the most important thing which makes sense in your case. Zipkin is not stopping you to put everything here, but it is going to hurt your performance just. Like if you log everything to the file, each and everything. Log, on the other hand side, they denotes something significant, or let's say an event name which marks the meaningful movement in the lifetime of a span. they are time stamped. So uh, uh, this information is time stamped and normal tags are not, and span may also contain 0 or more logs. Annotations are the one which helps to explain latency with a timestamp, and annotation are often codes like server receive, client send, which we saw on the previous slides. What are binary annotation? Well, they tags a span with a context, and usually they support a query or aggregation. One thing to notice here is that they can be repeatable and vary on the host. So for example, if we have http.path and we have URL rewriting enable on the server, so we will have a different value for the client and the different value for the server for the same thing like http.path. One question which pops up in our mind is, can we have a large span? Can we have spans which contain in the scale of megabytes? Well, Zipkin don't stops you, but we shouldn't do this. Why? Because it defeats, again, the purpose of tracing system. It decreases the usability and increase cost of tracing system. Uh, Beware of clock skew. Why? Because of the fact that computer clock ticks at a different rate. It doesn't mean my computer clock ticks at one rate and your will tick at the same rate. Maybe yes, maybe no. But when we are in distributed system and we don't take care of such things, then we may end up with some sort of clock skew, and due to this we can have some information presented in Zipkin which may mislead us and give us some false positives or negatives. How we can resolve this thing? Well, we can use tools like NTP, or if we have data center and we want to go something more fancy, we can install some GPS there and use them to make sure the end result is to make sure all your computer agree on the same notation of time. Tracer is the one which does the most heavy lifting work in entire this let's say tracing infrastructure. What it does, it creates the span, it takes care of context propagation, it takes care of passing the info between various spans. It is the one which need to decide, shall I create a new span, shall I create a child span, when I should calculate the time, so on and so forth. Sampling controls how much to record. For a high traffic system, it is advisable to record only a fraction of traffic. Why? Because if there is a problem, it is going to repeat itself. So it really doesn't make sense to record everything. On the other hand side, if you have a low traffic system, you have to adjust based on your needs. But remember, too high sampling, if your sampling rate is too high, then it is going to record everything, and it may add some additional burden. Sometimes we are faced with a situation that we want, no matter what, my span will get recorded, irrelevant of what is my sampling rate. So in this case, what we can do is we can mark the spans with debug equal true. What is open tracing? Open tracing attempts to standardize tracing, and it provides vendor-neutral tracing API. Implementation is available in 6 languages, and you can find more details here. Spring Cloud Sleuth brings distributed tracing to Spring World, and there is a project called Spring Cloud Starter Zipkin. So basically what it does is it takes the ease, it takes all the hard work which you had to do, and they did it and put it in and package it in a project called Spring Cloud Sleuth. So if you are using Hystrix or using REST template, then they take care of that, all the data between the spans get passed through. Now I would like to walk you through the code that I use for the sample demo application. And please note that I have created 2 applications. One is in Java and one is in Go. The purpose here is to show you that how to use distributed tracing when, let's say, if you have a out-of-the-box support for frameworks like Spring, which supports annotation and all these things. But in some cases, you don't have Spring. So what you do, so I will show you how we can create all this stuff via hand also, and how much difficult or how much easy it is to use this tracing stuff. So now we are at the code. So the first thing I have here is a catalog service. And as you remember, that create catalog was the thing which get invoked here. So if you see here, Zipkin find trace, then we have here, where it is, let's go here. you see here that we have here create catalog. So in the source code, if we take a look on create catalog, what happens is uh, what I'm doing here is I'm fetching a price, and if you take a look, what I do in fetching a price, I execute new trace command. This trace command is something which extends the hystrix command. So it extends the hystrix command and adds some span related information. So you have to use, if you are using hystrix, instead of hystrix command, you have to use the traceable trace command. And here I am using and calling under the hood a method fetch price, and fetch price is nothing fancy here. I'm calling rest template.get for object, and you know, the plain old Spring thing which most of you have used in day-to-day life. In the similar manner, what I'm doing here is I'm fetching the products here, and fetching of products, although it's a Go service written in different language, but from my perspective, it's just a REST call. So I'm making again a REST call using hystrix. So if something goes down, I will return some default results. And here I'm making some HTTP request, some REST request for this service running on localhost 8090. Lastly, I'm doing something in communication service execute in background, and what it does is, as you can see, if you have, let's say, something with asynchronous call, you can annotate in Spring using async, and async take care that some default things like name of the method, how much it takes, will get recorded. Last but not the least, let's say if you are using threads, if you are using threads here, so what we can do, here I'm using some executor service, and I'm using new processor. So as you know, for executor, we have to pass some runnable or completable. So here, what I can do, I can use also some annotation if you are an annotation fan, and you can tell your span foo bar or whatever. So that's how you can configure this thing. In price service, as you saw, I was calculating the price, and you saw that somewhere the cache was missed and somewhere the cache was not missed. So what is the logic here? Well, basically, I just created a simple hash map, and I just put on only one product there. And if the cache was missed, I just add something there. Let me show you one thing. Why what was the purpose of doing this cache miss? So let's say I want to go to a price service, and I'm interested right now to know that, well, give me everything from the trace where the cache was missed. So as you can see, I have two events here for which the cache miss occurs. But I'm interested even to narrow down my search, and I want to find only those traces where the cache was missed and the results were executed on cluster 1. Why we want to do it? Maybe we have some a Lambda running on AWS, and it is really expensive thing for which we pay, or we have some serverless architecture. So what we can do, we can use and enter here cluster equal cluster 1. And as you can see, it can narrow it further down. I can also narrow down here in Zipkin basing on the name of the service or the name of the methods. I can also write here my custom queries, or I can use these fields to say, well, give me all the traces where the request took greater than 1 second, 2 seconds, 3 seconds, so on. All right, so this was from the Java side, but we not all of us are writing everything in Java. We use various languages. So this is Go language. It's what I want you to focus is here. What happens is when I get a product handler here, I want to create a span from a request. So now I have a HTTP request. I have it accessible, and how I can create it. So what I need to do here is first thing I need to do is I'm using here open tracing APIs to extract from HTTP header the relevant bits of information. So I pass the request as a header, and I extract it. Then if everything, if I have a carrier and I can extract some relevant bit of context from this, and if it is not nil, means everything is, it is a new span, then I create a new span here. So it is an initial request coming here. But if it is a child span, so span was already created, then I can create using tracer.start span, and I can create a child span here. Once the span is created, what we need to remember is span denotes some time-stamped amount of work, which means that a span, when it gets started, it needs to be closed. Why is that? Because we cannot have infinite span. We can never work for infinity. We need to stop somewhere, and then the Zipkin is going to record. So if you forget to close those span, you may end up with a missing information. Why we were not doing it on the side of Spring? Well, Spring takes care of starting and closing the span. But if you want to start and close a span, even in Java using this API, then remember in finally you have to say that close the span. Otherwise, it will not get closed. And in Go, the finally is used by defer. So we say when this method exits, just execute this finish method. Then after that, what we can do is I try to log some event. So as you saw, logging of event means generating those so-called bubbles here, as you can see. So how we can generate them? They are the logs, basically. So I can use log event, and I can just pass the name of the event, and it simply gets logged. The API, the parent span, have the method log event. Then if I am calling some external service, let's say DB service, I can simulate. Here I'm just simulating something. What is important here is, again, I'm starting a span manually from some context, and I'm finishing it also once the method get successfully finish here. So this is all, I guess, which we can do in order to interact with span, create a span, and close the span. And if we want to set some tags, let's say when you are debugging something and you want, okay, if my query fails for some reason, I want to have my query, or I don't know, calculation time, something which is relevant during the debugging session, you can use set tag, and you can pass the name of the tag and some relevant bit of information. In the similar manner, I am calling the analytics service here, and oops. And here I'm simulating some analytics job. And as you saw in the logs there, I had this red type of span, which was denoting something is wrong or something like this. And in order to do this, we need to mark the span with an error here. And I guess this is it from the source code side. And now we are back to the slide. So you may ask, well, all right, it all makes sense, but who uses tracing? Does someone who is using it in production or not? There are really a bunch of companies which are using, some of them are using Zipkin, some of them have their own implementation of the same concept. For example, Uber have Jagger as an implementation, which is based more closely on open tracing. And there are some other companies which are creating either basing on Zipkin or creating something new. And you can see there, or using this URL, who uses the tracing. Zipkin and Prometheus, so I don't know how many of you are familiar with Prometheus, but Zipkin exposed the matrix which you can ask Prometheus to plot. Does Zipkin only supports Java, or only one more other language? No, it supports bunch of languages, and its support is increasing as the project is progressing more and more and more. If you are interested, for example, in not only tracing your Java code, but some machine learning or big data, Hadoop, stuff like this, there are also projects like HTrace, or Zipkin is also recently started to do something about in this direction. So the concept of tracing is not only relevant only for your programming stuff, in terms of application level programming. It is also related with the big data stuff. You can trace the calls there, because what you are doing under the hood is you are requesting something and the job have to finish and you need to get some result back. So the summary is that latency is never zero, and we should embrace it rather than rejecting it that, well, I really don't care. Distributed systems are really hard and complex. They are hard to reason about without any facts. Uh, Tracing can help to analyze end-to-end latency and understand call graphs, which means that we can have how my system look like when when this particular request was made. Instrumentation is tricky. You can say, well, why we should use Zipkin? Can't we write our own class and log all those things? Well, believe me, passing the context from one service to another is not so easy, and you have to take then into consideration asynchronous threads and all those stuff. OpenZipkin provides open source tracing system which helps to visualize the request flow. Spring Cloud Sleuth brings to Spring the distributed tracing, and Open Tracing is trying to standardize the tracing. Its goal is to standardize the tracing. So thanks all for your time. I think I'm not late yet. So thank you, and if you have any questions, I'm available here. All right, yeah? Pardon, could you repeat your question? I said something about? Um, you mean when?
Okay, so when you put the architecture on the slide,
All right.
you have the sampling box. Yeah.
All right.
The sampling.
Yeah.
So that means that not all the events that come into the system are logged.
Yeah,
or
because
traced.
because of the thing, one thing we can do is using a sampling. Another thing is using debug. And so, if you have debug enable, then we have to force them to be logged. And what I wanted to explain using this diagram is that when we use sampling, we can control what to store.
Okay.
Yeah.
So that means that tracing sometimes can bog down a system if the rate of the events is too high?
Well, because under the hood, that's why you see here that it try to schedule for storage. It don't really stores at the moment. It schedule it for storage. But if you will pump it, even if you have Ferrari and you pump it extremely well, it gets out of control. So the same happens here, that it try to schedule and it try to be clever that you can get a bit higher in sampling rate, but at some point you have to make a decision. If you have, I don't know, millions of requests coming in a second and you want to log everything down, then maybe things will start to get a bit clunky there.
Okay, understand.
All right.
Thank you.
All right, so I guess that's all. Thanks.